All right. Good morning, good afternoon, everyone. Thank you all for joining us. My name is Jared Cohen. I'm the Marketing Communications Manager with Parker Chomerics. And thank you for joining our webinar on Premier Electrically Conductive Plastics. Just give everybody about 30 more seconds to join up. I see the attendee list is starting to grow here, so give everybody about 20 seconds or so before we start. Thank you. All right, I have 11:01 Eastern, so I think we are ready to go. And we'd like to get into a little bit of some housekeeping details just to start us off. So at first, please set yourself in listen-only mode if you haven't already. You should have joined as listen-only. We will be taking questions at the end of this session in our question and answer session. So on the bottom of your Zoom screen, you should see a question chat or Q&A button. Go ahead and type in those questions, and at the end of the webinar, we will get to them in the order they were submitted. And then finally, this webinar will be recorded and available after the call. You will automatically get it within 24 hours, the recording, and any additional documentation. So please look out for that. And let's get started. All right, so I'm going to introduce today's speakers, starting with Sierra.
Hello, everybody. Thanks for joining. My name is Sierra Eiden. I'm the Defense Aero Market Manager for Chomerics, and I've been here about 10 years.
Hello, everyone. My name is Ben Nudelman. I'm a Market Development Engineer for Chomerics, and I've been with the team for about 3 years.
Hi, everyone. I'm Peter Torok. I'm the Plastics Product Line Manager. I've been with Chomerics about 16 years and working in the plastics marketplace for about 25 years.
Excellent. Thank you, guys. All right, so we'll get into today's agenda. We'll first do a little bit of an introduction about who Parker Chomerics is, and then we'll get into an introduction about electrically conductive plastics and different types of conductive plastics. We'll then talk about secondary benefits such as assembly and manufacturing, and then get into the meat of the application examples. And we'll do a final summary and plastics review, and we'll get into the all-important question and answer at the end of the session. So like I had said earlier, go ahead, as we're going along, if you have a question, go ahead and type in the question and answer box, and we will get to that question at the end. All right, so who Parker Chomerics is. Parker Chomerics, if you don't know, we are a global leader in the premier material solutions. Our core competencies are in material science and process technology, and we really have a market-driven product development cycle with vast product technologies, including integrated housings and displays, custom engineered solutions, and global supply chain management. So Ben, I think with that, we should get into introduction to conductive plastics.
Yeah, Jared, thank you very much for the introduction, and let's get right into it.
All right, guys. So when we're here today to talk about the benefits of using conductive plastics. And one of the things we want to talk about is more specifically is lightweighting. What do we mean by that? So most plastics will weigh about half as much as aluminum and as low as about 20% of the density of steel. So the density range is about 1.3 to 1.4 grams per cc for most conductive plastics. Aluminum is about 2.7 grams per cc, and stainless steel can be upwards of 7 grams. So when we talk about lightweighting, it's a huge, tremendous benefit. Elimination of hardware. There's a lot of things you can do when you design these plastic parts strategically. So you can add features like snap fit mating surfaces that'll give a permanent sealed part without having mechanical fasteners like bolts and screws, which add weight. Snap fit housings can be not only a reduction in cost from the permanent removal of hardware, but also reduction in total assembly time, reduction in weight, leading to an overall reduction in complexity, which is, the ultimate goal there. The other thing is you can eliminate a lot of the secondary operations, such as machining of die-cast housings to, achieve tighter tolerances. You can replace machine holes with thread forming screws. And you can also mold with no machining for really high tolerance fits when it comes to under an inch diameter type designs.
So building off of that a little bit, instead of machining several parts, the nice thing about plastics is that you can mold a single complex geometry in a single go. So what that means is that the tools can include very thin walls that would typically require hours of machining or several sheet metal parts. Additionally, tolerance control with conductive plastics or plastics in general is on par with the highest of machine parts. So you're looking at tolerances of 1 to 2 thousandths, and actually far more accurate than what you would see with die cast and sheet metal parts. Additionally, while the tools for plastic parts may have an upfront cost, they're going to last nearly 10 times longer, yielding upwards of 1 million parts before scheduled maintenance instead of in the tens of thousands with things like die cast.
Yeah, and we realize that, not everyone on this call is going to be designing parts that are, millions of parts. It might be the thousands. So you can actually get away with designing like a modern aluminum tooling with some hard coats that you can use for low volume production, in the thousands of parts. So you can kind of get away with that.
So let's talk a little bit about why conductive plastic should be used. There's a long list of benefits that goes beyond just the basic benefits of metal to plastic conversion. So as opposed to metal-based housings or plated plastic housings, conductive plastics actually include an absorptive property that reduce the amount of EMI energy transmitted throughout the housing. Additionally, you're looking at the fact that conductive plastics can withstand a lot of repeated drop testing and impact testing without damage.
So the other thing is you can, eliminate things like, say you're going to mold a plastic part. So I had a customer once that had a 2-part clamshell design. It was a non-conductive plastic. They were coating it with a conductive copper paint, and they were getting a lot of resonance and bounce back from the signals inside. So they actually got some pellet samples, molded a conductive plastic part, and because of the absorption properties, they reduced the steps in their design. So they eliminated the masking, they eliminated secondary absorber pads. There's also a lot of dimensional benefits to conductive plastics. So the goal is always to get closer to a shoot and ship part. You want to get there to 0 defect manufacturing. So you can do that through process monitoring, where you establish the molding parameters. You can get very consistent part-to-part results. You can also minimize variation from shot to shot, dialing in those process parameters. When you think of a machined tolerance on a diameter of, say, 12 millimeters or like a 1/2 inch hole, you can actually get plastic parts to vary by less than 10 microns on small parts like that. And, this isn't utopia. This is just good upfront planning. And then also conductive plastics come in a variety of materials that can be meant for chemical resistance, resisting harsh environments. As we know, corrosion is a huge issue. We'll talk about it a little later, but this is the only material tested that showed 0 corrosion with a specific customer that we'll talk about later.
So talking a little bit more about really what the secret sauce is to our conductive plastics. And while we're going to mention it a few times throughout this presentation, the Chomerics trade name for conductive plastics is known as Premier. So when most companies talk about using conductive plastics, what they use is actually a non-homogeneous blend of pure plastic pellets with metallic conductive slugs. The problem with this process is that it can actually include a lot of inconsistency in the molding process and inconsistent electrical and physical properties of the complete part. Premier pellets, on the other hand, actually use a long fiber pultrusion process. And so what that means is that you have a conductive fiber running through every single pellet, in addition to a proprietary dispersion agent. So what you're getting with that is actually optimal electrical properties and consistent parts from batch to batch across thousands of parts.
Okay, so Ben, what is the specific materials used and why does the pultrusion process matter?
Yeah, it's a good question, Sierra. So we use a nickel-plated carbon fiber, as you can see here on the slide. And the pultrusion process actually leads to a uniform fiber dispersion throughout the part. So because each pellet not only has the same amount of fiber, but is actually the same size, all the final parts will have a very consistent conductive composition. And here is just a little bit more about what I was talking about. So on the left, you see our premier plastic pellets that have that fiber running through the middle, whereas on the right, you'll see a multi-pellet blend. And so you'll see that there's different sizes of the plastics, as well as the inconsistent mix of some of the metal slugs.
And some people in plastics call the multi-pellet blends, they call them cube blends, or they call them salt and pepper blends. So you'll hear those terms used quite often. And, you know, they'll get you some kind of decent results for the most part. But the problem with this type of blend is the fact that you can never guarantee a 100% perfect mix. There's always going to be some settling and some inconsistency of the conductive material to the non-conductive material.
Exactly. So in the process of things like transporting the material, a lot of the times the metal slugs will actually vibrate and sink to the bottom of the packaging. And at that point, you know, early shots might have a much higher metal composition than later parts.
Okay, so we get right into the sweet spot in conductive plastic design. So there's a couple things to consider. Conductive plastics work very well when they're designed in the sweet spot, the geometry, the molding parameters, but keep in mind parts should have a 1.5 to 3 millimeter wall thickness. Ideally, they have to be consistent walls. You don't want, you know, different thickness walls. Obviously, that's just a regular plastic molding thing anyway, and you also don't want the part to be too much larger than 150 grams. So the larger the part, the lower the cost performance. It's one of the sweet spots.
And while there is some upfront cost in buying an injection mold, there are a lot of volume-based benefits for programs that require higher volumes. So for example, working with an injection molding partner is actually the best course of action, especially with those partners who often work with engineered polymers. And depending on the volume and complexity of those parts, Chomerics can be a partner. So not only do we manufacture the conductive pellets, but we can also do the molding in-house.
Yeah, and so, you know, you're going to see diminished properties at lower temperatures below -20°C. There's also limits to outgassing, but this isn't specific to conductive plastics from Chomerics. This is across the board, you know, so there will be limits to that.
And finally, the last little point to point out on the sweet spots of conductive plastic design is that we actually don't recommend molding a bulk sheet or machining pieces of conductive plastics. And that has to do with the variation in fiber direction once you start machining the parts.
Yeah, you want to make sure that the fiber, the conductive fiber, is always parallel to your wall thickness. And if you're molding a block and then you start hogging out that block, you just can't guarantee that. And as soon as the fiber is perpendicular to the wall thickness, you start losing shielding effectiveness. So we definitely don't recommend that.
And now talking a little bit more about the base polymers, we're going to talk about the different types of conductive plastics we have and their benefits. So there are actually three main base polymers in our premier conductive plastic product line. Each has a different specific property, making them ideal for different applications. So the first one that you see here on the left is a PBT. It's a polyester base, and it was actually specially formulated for chemical resistance in automotive applications. So specifically resistant to automotive fluids in underhood applications. And the two different types of PBT materials are a PBT 225 and a PBT 250 FR, that FR being a flame retardant variant. In the middle, you have a PC ABS, which is a polycarbonate ABS alloy. And that actually has a few different grades, and it's a great cost to performance value. So A220, 230, and 240 represent the different loading levels of conductive fillers within the polymers, with a high temperature and flame resistant variants available in all of those. And finally, you have a PEI on the right side, which is a polyether imide, or an all-10 based polymer, which is actually primarily used for high performance military applications or applications where you see high temperature requirements or where optimal smoke density performance is needed.
Yeah, and just to point out, you know, the PBT family was a recent addition to the family of polymers. If you think you need something and you don't see it on the chart, please reach out. We design and develop materials constantly. So if there's something you're looking for specifically, please let us know. Okay, so this is a big chart, and of course you'll have this after the fact, but this is just something to show, you know, for instance, the PBT and the PEI are very excellent at chemical resistance. You know, automotive applications under the hood, you're gonna have to resist automotive fuels, defense aerospace, you know, you might be resisting jet fuels or hydraulic fuels. You can see EMI shielding on the PCABS A240 is high. So, you know, it just depends on specifically what you're looking for. But if you're unsure, we will always work with you to make sure you get the right material. We're never going to tell you to buy the Porsche when you just need a Yugo. And we do provide test sample boxes of pellets, as well as boxes that you can actually, you know, put your cell phone in and call. So.
Yeah, we have a variety of different samples that you can buy through our website, through our parker.com e-commerce site. Like Sierra was saying, there's test boxes where you can put your electronics inside and do some actual real life EMI shielding tests. And also keep in mind what Sierra was saying before, you don't have to know this from the presentation. This is just something that gives you just a quick user guide, just a feel for the fact that there's a variety of materials out there, and you don't have to be an expert in what each one of them does. We'll help you navigate those waters. We'll help you figure out what's the best material for your application. So it looks intimidating, but don't sweat it, because we're here to help on that.
Thanks, Pete. Okay, so PCABS is by far the largest polymer family that we have. There's 3 grades, but there's also subgrades within the family. So HT is a general all-purpose material. It's most economical. You get into an FR, which is a flame retardant. It's a V0. ST is a tougher material for impact resistance, and also has a higher maximum operating temperature. And the HT and the FR actually have hybrid fillers. So what this does is improves the cost performance and also reduces warpage. So these are actually the standard nickel plated fiber that we pultrude and actually pelletize into each. And then they backfill it with granular fillers to basically make it more filled with material. So
yeah, nickel plated graphite is also used, and like Sierra was saying, that's going to reduce the warpage. It's going to give you a little better cost performance without sacrificing the shielding. And then last but not least, the ST, the super tough, the way it gets to be super tough is we're using more PC in the alloy and less ABS. PC is a highly impact resistant material, you know, like your safety goggles are all polycarbonate. And using more PC, you're going to get better impact performance, but you're also going to get better impact performance from being an all fiber material. So that doesn't have any of the granular fillers. So all that fiber, it's like a carbon fiber reinforced material. We've had customers that made boxes and they dropped them 30 feet on concrete floors, and the boxes have survived great. You know, the electronics might have got a little messed up on the inside, but the boxes were great. So, I mean, there's a variety of different materials, even in the PCABS family, you know, and we're always looking for where we can give you the best cost performance without sacrificing your other needs. So we'll help you dial that in.
nice.
The next thing we want to talk about is actually the comparison of conductive plastics versus some conductively coated plastics, and what those applications look like. So in addition to conductive plastics, there are actually non-conductive plastics that can be plated or have coatings applied to help them meet some EMI or electrical standards. The most common one is actually taking a non-conductive plastic and coating it with either an acrylic, a polyurethane, or an epoxy-based conductive paint. So conductive paints are actually the most cost-effective solution to apply onto large surfaces and flat panels of EMI shielding. And a lot of that comes back to the fact that, like we mentioned before, it's very difficult to mold large surfaces and flat panels in conductive plastics. The next category is electroplating, and it's actually used to apply a very thin metal layer, and it can provide a very, a moderate shielding performance and some aesthetic properties. And finally, we've got vacuum metallization. It's another method of coating non-conductive plastics, but it's not necessarily suitable for EMI shielding. A lot of the times the vacuum metallization is used for decorative work or mirroring. And really the reason it's not used for EMI shielding is because it's a very, very thin coating. So less than 1 micron thick.
Basically, if you try to vacuum metallize a super thick coating, you'll take the plastic to the threshold of melting. So the way that people get EMI shielding out of vacuum metallization is they'll actually give it like a dose of metal particles, let the part cool down for a while to give it another dose. So sometimes that could take 2 or 3 applications to get to the thickness required for EMI shielding. So that's why we say, even though the process itself will get you there, it's just not an economical way to get there for EMI.
Yeah, and while coated plastics can meet the EMI specs, they work very differently from conductive plastics. And I'd mentioned the clamshell design with the non-conductive plastic coated with a conductive copper that the signal is bouncing inside. Conductive plastics actually absorb incident energy instead of just reflecting it. So with conductive plastics, the shielding mechanism is actually built into the part with very high levels of consistency. So, you can drop a part and chip a piece off. It's not going to affect the shielding effectiveness as if you had taken a non-conductive plastic part, painted it, dropped it, scratched it. Now you have to go back and touch it up. And so, there's a lot of variation from coating processes as well. Vapor dep is a line of sight. So, you can't, you're just going to spray it and it's going to hit whatever surface is coming up. So, back in my former years, in my former life, I was a paint person and I designed electronics, and I noticed a lot of variation coming from this one facility. So I went to investigate, and it turns out on the first shift, the guy was 4'7", and on the second shift, the guy was 6'7". So we had a lot of inconsistencies just because of the height of the guy that was painting the parts. You never know what you're going to find.
Yeah, plus keep in mind that any type of coating process is going to have yield loss. I mean, that's just part of the nature of that type of manufacturing process. So you're going to have to deal with not only yield loss, but you have to figure out which parts in your manufacturing batch have defects. So you are literally inspecting every single part using, in general, human vision to find out if that's a good part or a bad part. So, can you get there? Yes, you can absolutely get there, but it's a very labor-intensive process, and it's very subject to the potential for defects. It's just the name of the game. You can't avoid it. And that's one of the things we say about conductive plastic. Sometimes on first pass, it's not the most economical solution, but when you start figuring out all of the yield loss and all of the inspection and all of the failure costs and things like that, sometimes you'll find out it's a very cost-effective solution.
Yeah, and to get into some more of the technical information, the next few slides are actually going to be shielding effectiveness performance of conductive plastics relative to conductive paints, relative to vacuum metallization. So this slide, just a quick overview, we've got the 3 grades of our PC ABS, the A240, the A230, and the A220. And you see the different shielding effectiveness across the frequency spectrum up to 18 gigahertz, with the higher grades providing you with an average of almost 100 dB of shielding. Once you get into conductive paints, you're in the mid 50s to mid 70s range, again, across that entire frequency spectrum. And this is 2 of our co-shield conductive paints. And finally, vacuum metallization. It really doesn't matter what type of metal, whether it's an aluminum or a copper or an aluminum copper blend, you're in that mid 50s, 60 at best across the entire frequency spectrum. Finally, before we get into some of the different applications, we're going to have Pete talk about some of the molding parameters and secondary assembly processes.
All right, thanks. So as Ben was saying, there's some benefits to conductive plastics that we're going to dive into here. And so the good news is that conductive plastics in general are not difficult to mold. The materials that we're talking about here, these premier materials, and you can use standard injection molding equipment. There are, however, some specific molding techniques that you really need to use to get the best bang for your buck as far as using this material and molding this material. So one of the most important things to remember is that during the molding process, you want to bring the fiber in granular fillers right to the surface of the part. So this is kind of the opposite of what people are doing with most other types of engineering materials. A fiber-rich surface ensures you're going to get maximum conductivity and maximum EMI shielding performance. Now, I don't know if it was Ben or Sierra, but one of those two alluded to the fact that you're going to get absorption with this material, which is this nice benefit, but you're also going to get a reflective surface. The more fiber you can bring to the surface, the more you're going to improve that reflective nature of the product itself. So the goal is to bring as much fiber to the surface as possible. You're going to get the absorption no matter what, whether it's at the surface or inside, but you're also going to maximize your EMI shielding and you're going to maximize your conductivity. So what does that mean? You're going to get a better grounding of your housing to like the ground trace on your circuit board. Like I was saying, this is kind of the opposite of what most people do with like a glass-filled nylon. So a lot of tools and things like that have glass-filled nylon housings, like if you buy a DeWalt drill or something like that. So that's when you look at the surface of that part, it's like, hey, cosmetically, it looks pretty good, and this is a 30% glass-filled material. Well, those people are processing for a resin-rich surface. You're going to want to do the opposite with this material. You're going to want a fiber-rich surface. So another area you want to make sure that you have covered and you understand you're getting your best performance is you want to take a little time to make sure that the injection unit on your molding machine is properly sized. And basically, ideally, you want about 3 to 4 shots in the injection unit. So say you have a 4-ounce injection unit on your molding machine, and the shot size of your part or your parts is 1 ounce. So that's ideal. So then you know that by the time the molten plastic gets to the nozzle and gets injected into your mold, it's properly processed. So the material's melted correctly and it's had a chance to get mixed inside the injection unit. And the flip side to that is you can't hold the material forever because like most polymers, you start holding it longer than 5 minutes, you will degrade the material. So it's a little bit of a balancing act, but it's not difficult. This is the same kind of thing that people will do when they process time-sensitive materials like PBT. And your properly processed part will always have this kind of a mottled appearance to it. It's never going to be aesthetic. It's actually kind of cool looking. And under a microscope, you'll see the fibers like you do right here. But that's what good looks like when you properly use these materials. And last thing you want to remember is that if you follow these guidelines, you're going to get really good performance. If you don't follow these guidelines and say you process a resin-rich surface, what's going to happen is you'll be buying a 240 material, you'll get EMI shielding like it's a 220 material. So all you're doing is kind of hurting yourself as far as cost performance. So it's important to make sure you follow those guidelines. Next slide. All right, another thing I just want to touch on real quickly is beyond the obvious benefits of lightweighting, one of the biggest advantages with conductive plastics and plastics in general is the simplification, reduction of the supply chain. So, mainly this is achieved by reducing or eliminating secondary machining or manufacturing or assembly processes. One of the most common ways people do this, and Sierra talked about this earlier, is you'll either insert mold embedded fasteners like molded and threaded inserts, or you can eliminate that completely by just molding a hole and then using thread forming screws. That's where you're going to get to like the ultimate best cost performance. And this is the opposite of what people are doing with die cast parts. They're usually die casting a part and then secondary either drilling or tapping or both. So another technique that's used quite often is welding. virtually any type of welding that's done with plastic, you can do with conductive plastics. So, you can use vibration welding, hot plate welding, UV welding, laser welding, and ultrasonically install parts together. To give you some idea how much savings you can achieve, a perfect example is a radar sensor housing. So like the little box that detects your blind spot in your car, that little light that shines on your side view mirror. So that's your typical radar sensor housing. The earliest versions of those housings were like die-cast parts that had a plastic radome that was assembled using metal clips and complex gaskets. Today's versions are all basically a conductive plastic housing with a non-conductive plastic radome that's radar transparent, and then it gets laser welded together. Your typical program for an automotive sensor housing, I mean, you're literally saving millions of dollars a year on just one program by making that change to go from gasket and clip assembly to laser welding. So the cost savings are like phenomenal. And then there's the snap fit, which again, Sierra talked about earlier. And we'll talk about that a little more on the telecom faceplates. But that's the elimination of hardware altogether. So that's your ultimate goal. If you can eliminate hardware and you have a chance to do it with plastics, you definitely want to go there, because that just improves your supply chain. Now you don't have to make sure you have screws stocked all the time. You don't have to make sure all of your screw assembly equipment, screwdrivers are all torque set and everything else. You're just taking part A, part B, and most of these things you can assemble by hand without any special equipment or anything, and they just snap together and they stay together. These are obviously ideal for like a non-environmental seal, right? So you're just joining part A to part B, and you're not trying to achieve like some super great environmental seal. But that will cover a huge amount of plastic. And then as we go through these things and you see some of these examples, keep in mind that you have application support with Chomerics. So I'll be available for the questions at the end of the webinar. And, we're here to help you as you go through this journey, as you're trying to convert metal to plastic. And, we'll support you along the way. Make sure your plastic part design is solid and you're not making any mistakes. And make sure you're getting the best potential usage of things like snap fit and elimination of secondary operations.
So now we're going to get into just a quick review of a few of the different examples of applications that have been used with conductive plastics, and then finally get into a summary in our Q&A. So this is a perfect example of a use for conductive plastics. It's a man-portable handheld device or a handheld radio. And as you can see here, we were able to mold the entire part in a single process with a lot of the complex geometries that would require a lot more machining in metal parts. Far simplified here. Additionally, we were able to incorporate a shielded window. And as Sierra mentioned, this part was buried for environmental testing, and it was the only part that didn't experience any kind of corrosion. Finally, we integrated thread forming screws and eliminated a lot of the machining operations that goes into a lightweighting of a part like this.
Oh, and board level shields. So we've designed hundreds of board level shields for customers over the years. One thing is you can shield components from each other. You can shield cavities of your circuit board different ways. You can put a lid or a can on top. But you have issues during drop testing where the lid or the can may break off at the solder joint because of impact. And the other thing too is with being able to mold a board level shield, you aren't limited in your geometry like you are at the mercy of bent sheet metal tolerances, or the expense of very expensive machined aluminum housing. So these can be very, very useful. The other thing too is that a lot of times you have to put some secondary absorber pads, and this being an absorptive material can also, many times you actually eliminate the absorber pad. So board level shields can be a very good solution. So missile guidance systems, I mean, we all know electronics are getting smaller. The seeker head of a missile, you're trying to compact a lot of electronics inside, you know, the camera systems, the fuel. You can take little tiny parts that used to be maybe a metal clip and you mold it out of plastic. You know, you're reducing weight, you're compacting the housing design. It's a lot of weight, of space savings, and you can do really unique and exotic geometries. So it's pretty interesting.
Yeah, and I alluded to telecom faceplates when I was talking about some of the other examples of how we can save customers money. So the part you see in the picture is actually a fiber optic faceplate, but one of the first areas we actually had really good success in was filler panels. And filler panels are basically just faceplates and air baffles that occupy unused slots in like a card rack for telecom. And they used to be made with extruded aluminum for the faceplate and then a stamped sheet metal air baffle for the baffle that went behind it. And that air baffle was just basically resisting airflow so that the air didn't blow by all of the live cards. It had uniform airflow across. And we were able to come up with a way to make the air baffle out of non-conductive plastic, because that didn't need the EMI shield, and the faceplate out of conductive plastic, and basically three parts, just a label, PSA attached label for the front that had color and text on it, a faceplate that was EMI shielded, and then the air baffle. And then we made a snap fit design. By going to a snap fit design, we're able to improve the cost of the aluminum extrusion and the stamped metal. We were like 50% of that cost right out of the gate. So, I mean, there's huge benefits you can gain if you use the right techniques and you use the right materials and you kind of put it together for the most cost-effective way.
So finally, we're gonna go through the best uses of conductive plastics in a summary of what we've talked about, and then get into some of your questions. So the first one that we've mentioned several times is obviously that weight reduction. So if you have the opportunity to reduce weight by more than 50%, 60% by transitioning from a metal to a plastic, conductive plastics is really an opportunity that you should take a look at.
Yeah, next would be part size. So if you have if your part is less than 150 grams, if you have thin walls, you know, this is an ideal candidate to shield and lightweight.
The next ideal application or the benefit is the minimizing of secondary operations. So minimizing machining, minimizing some of those, the hardware and fasteners that go into it through things like snap fit and complex geometry design.
Yeah, and we've talked about high volume consistency, and I'll say any consistency really. It doesn't have to be high volume, but you know, the ultimate goal is to get to shoot and ship. So, you know, machining, die casting, you know, those all, I think plastic molding is just an excellent solution for consistency.
Another benefit, depending on the different polymer bases that you're looking at, would be impact and environmental resistance. So super tough material that can be dropped from 20, 30 feet, as well as materials that can withstand automotive fluids, environmental changes in temperature, as well as harsher cleaners and chemicals.
And of course, high frequency EMI absorption, that's what, you know, we're here for. That's what Chomerics does, is we shield devices with materials. And so, like I talked about, this material actually absorbs the incident energy. It also absorbs, you know, the RF energy, and it reflects as well. So it's a very good shielding material and reduces and eliminates absorber pads, which is just one more thing you got to think about.
So,
and that is it.
Yeah, with that, I think we're going to get into some of the questions. Thank you all for submitting them. Feel free to keep submitting them. Please use the Q&A function, and we'll have Pete start getting into some of these questions.
Okay, you want to start, Ben, or you want me to start?
I can start. So we have a question from Paul that asks, what is the conductivity between two molded parts, assuming resonance contact geometry? Pete, can you talk a little bit more about that?
Reasonable.
Yeah, so in general, you're going to want to use gasketing, because we've had customers before mold a board shield and then just use some sort of like a compression achieved by just assembling the housing together. So they've actually had some success doing that. But if you're looking to EMI shield anywhere in the 50, 60, 70 dB range, you're going to want to use gasketing. So you know, it's the conductive plastic, although there's a lot of fiber on the surface, it's still inconsistent and it's still hard to achieve a very uniform conductivity, like say with the ground trace on a circuit board. So it's just the name of the game. And you would want to do that for a metal housing as well. It's just the way it is.
Okay, I'm going to skip down to the next, Alex, and I love when Pete answers this question. It's the best. What are the material comparison in thermal capabilities? Heat capacity, thermal conductivity, thermal expansion. This is always a good one. I love this.
All right, so in general, conductive plastics are about 2x the thermal expansion of most metals. So depending on what your design is, like say you had a heat sink and you had an idea you're going to take that heat sink and you were going to mold it into a housing, and then you're going to mold around it. So if you're trying to temperature cycle from like -40°C all the way to like +80°C, the plastic's not going to survive that. So you have to allow for some sort of expansion between the heat sink and the plastic. And there's ways we can achieve that. We've done that with like RTB compounds and things like that. But yeah, that's in general one of the CTE mismatch between plastic and metal is something you definitely want to keep an eye on. And then as far as I don't have the numbers for specific heat, but we have a lot of that data in our applications engineering department. We can share that with you if you need it.
Pete, the next question comes from Mark. It says, other than automotive and mil aero, what are you seeing in terms of applications for this material?
Well, there's been a lot of interest in the battery market lately. And like, for instance, there's people who are really big on flow batteries. I don't know if many of the people in the audience are familiar with that, but one of the most effective ways you can store a lot of electrical energy is with this setup where you have like this tower of fluid, electrolyte fluid, and you charge that fluid and discharge it by going through a flow battery. And one of the keys to a flow battery is having thin panels of conductive material that the ionization can occur through. So there's been some success using conductive plastic for that. We've also, like I said, had a real good success with, in general, EMI shielded housings in a variety of markets like telecom. And we even had a customer that had a housing that went around a display terminal that went on a gas pump. So, so that type of market's also very viable. That was a good one for our PBT material. We've also had customers that wanted to use this material just as a conductive plastic that you can use on a touch screen, where you just grab a little plastic stick and you use that to, instead of touching the touch screen with your finger, it's the COVID safe way of using a touch screen. So, I mean, there's a variety of uses, and we're seeing new ones every day.
Okay, so this question's from Dan, and I think I'm going to take this one, Pete. Would you explain again the potential advantage of absorption over reflection? So, you know, back in the day, you design your electronics box, you'd paint everything copper inside, and you'd shut the lid and it'd be fine. But nowadays, you know, you have a circuit board with a GPS chip, a Bluetooth, an antenna, you know, and these chips are actually interfering with each other. So part of the absorption advantage is that the signal's being absorbed, it's not reflecting inside the box. So it's really, when we talk about the potential advantage of the absorption of the incident energy, it's really, I believe, mostly related to internal components. I believe if anybody wants to back on that, but I think that's pretty much the idea.
Yeah, and then on the thermal management side, like the radar sensor housing. So in general, these materials don't have spectacular thermal conductivity, but people have successfully built little boxes that are like the size of a deck of cards that have a 3-watt system inside, and they're able to just use a thermal pad to use the housing as a heat spreader. So even with a relatively low thermal conductivity of like 0.7 watts per meter K, the housing still functioned as a heat spreader in a low wattage system.
Pete, the next question, we've got a similar question from Thomas and from Michael. What's driving the max temperature in the material composition chart, or the material comparison chart, or where along that max temperature range is a part going to fail?
Okay, there's a test that you'll see on many data sheets for like UL. It's called RTI. And I think it's relative thermal index. I'm not positive right now, but basically it's a test that says, okay, I can operate at a max temperature of 100 or 105 C, and I don't have to worry about the material basically twisting or yielding or basically not performing for me. So it's kind of a max operating temperature. And what's a little tricky is the PBT materials are actually listed at 75 C, but in reality, they're probably closer to like 120 or 140 C because we don't have the RTI testing for that material yet. And they just assign you a general purpose number, which is comes from an unfilled PBT material. And this is obviously a highly filled PBT material. So this has much more performance. So RTI is one of those areas you want to kind of keep an eye on, and that's kind of like your best rule of thumb for maximum temperature. Now, obviously, if you have a system where something's going to expose to a high dosage of heat for just like 10 seconds at a time and then dissipate really fast, that's not the same thing as RTI.
Okay, question from Paul. Regarding the fiber-rich surface, what are general process parameters that enhance fiber at the surface, specifically at joints between parts?
Oh, it's all about mold temperature. I mean, that's really the ticket. I mean, so the two things we've noticed that actually give you the best fiber at the surface is you want to run your coolest possible mode. And obviously you want to make sure you're still filling your part and packing out your part. You're not sacrificing anything from the processing side from that end. But as long as you're doing that and you're running a mold, say, for instance, PCABS, if you were to look up a general purpose PCABS, it would tell you to run your mold temperature at about like 170 degrees F to like 190 degrees F. When you run Premier, that's PCABS, you want to run it down around 100 to 110. And you're going to sacrifice a little bit of material flow by running it that cold, but you're going to get this great fiber-rich surface, which is going to give you that maximum reflection and maximum conductivity. So the other thing that we noticed does help a little bit is if you can inject the material slower, you'll also get a little more fiber-rich. But obviously, the name of the game in most plastics is you want to inject the material and fill it as fast as possible, because that's going to give you your most consistent processing. So I always tell people, strive for your most consistent processing and then start turning down your tool temperature. And then if you start to lose like fill and things like that, you notice that at 100 degrees F, you're starting to non-fill and things are starting to go wrong. So then you would bump it back up to like 120 and, you know, just maintain your temperatures likewise.
Gotcha, Pete. Thank you. And we've got another question from Jeff on a similar note. What do I do with all the heat inside my enclosure? Can I sink the heat to Premier Plastics?
To some degree, you can. Okay, I mean, you're gonna. So an important thing to remember is the size of your housing is going to act like a big heat spreader, right? And we only list the through conductivity of like 0.5 to 0.7 watts per meter K. But inside the housing, you're getting in-plane conductivity that's about 10 times that high. And you know, it's all about making your housing a heat spreader. So it's one of those things that you should always strive to use as much thermal material as you can to transfer from the hot chip to the inside face of the housing. And we've actually had some pretty high wattage components. I think we've gone up to like something like 7 or 8 watts in small housings and been successful. But in extreme cases, we actually have developed a kind of a new approach called the hybrid housing, where we have, and I touched on this earlier, we have a housing with an opening in it, and the opening has a die cast heat sink, and then we come up with a way to snap fit the heat sink into the housing and then use like an RTV compound to environmentally seal that in. So that's been pretty successful for applications where you just can't get the housing to dissipate enough heat.
Okay, so there's a question from David. Are there any issues associated with adding other fillers to master batches? I know we do things like clariant dye, but what else, Pete?
Yeah,
Are there
well, coloring this material is never a good idea. Let me just start with that, because basically you're looking at a material that, you know, in essence, you're about 10% to 30% carbon filled. And, you know, even with the nickel plating in there and other ingredients, as soon as you put that much carbon in the material, it's like really, really next to impossible to color it. So as far as coloring, you can pretty much cross that off the list. If you have to have an aesthetic outside surface, then you'd have to think about a painting operation. Other ingredients, I don't know. I guess we'd have to try those, you know, master batching. Remember, master batching is that thing we talked about earlier where you're dry blending in other pellets. And anytime you do that, there's always going to be some variation in the mix ratio. So that's, you know, depending on what you're doing and what you're trying to achieve, sometimes that's risky and sometimes that's not a big deal. Like if your color is off by a little tiny bit, that may not be a showstopper. But if you're trying to achieve some kind of a performance, like for instance, if you add a hydrolysis resistant additive to something, you know, you master batch that in, there's always going to be some risk. So be careful with that.
Thanks, Pete. So we've got about, looks like we still have about 20 questions and about 10 minutes before we want to wrap up and end this webinar. So let's see if we can quick fire a few of these questions.
Okay.
Pete, can you talk, Glenn asks, can you comment on shielding for low frequencies?
Yeah, one of the things about a lot of this nickel plated fiber is, you know, you start to drop off the shielding once you get into the, you leave the megahertz range, you're into the kilohertz range, it starts to drop off into like the 30s and 40s. And there's a test, there's an ASTM test, which I can't remember the number right now off the top of my head, that, you know, in general, we're in the 60s on that test, but that's not the same thing as the panel test, the IEEE test. So if you're really looking for very robust shielding in the kilohertz range, this material's, you're gonna have a little bit of trouble getting above 50, 60 dB. I mean, that's just the nature of this material. You can't put enough conductive fiber in it to get like a super robust shielding product in that low frequency. It's all about metal when you get that low frequency, and you can only put so much filler in a part like this, a material like this. So that's one of the compromises. Next.
Oh, okay. So we got a question from Jeff. What types of gaskets can be used at interfaces? Fabric over foam, beryllium copper? Yes, yes, and yes. Conductive elastomer.
Yeah, most gaskets,
epoxies, anything. So
yeah, remember the filler materials in this are nickel, stainless steel, and carbon. So anything that'll galvanically work with nickel, stainless steel, and carbon is a good choice. We've had people use finger stock, fabric over foam. We use a lot of different extruded gaskets, a lot of Chomerics gasketing there, FIP, and even the stamped, like soft shield. I don't know what it is right now off the top of my head, but where you take the sheet of material and you stamp out a gasket and it has Z-axis compression. So those gaskets have worked as well.
We have a question from Jeff that says, are quick turn injection molding techniques possible? Example, aluminum molds.
Absolutely. Proto Labs, like I would say they're the leader in quick turn injection aluminum molds. They used Premier like on dozens and dozens of different projects. It's very successfully. They're very familiar with our products, and they do a lot of prototyping. So yeah, those are very, very usable, and they get very good life out of their tools. I'll give them credit. They're probably a leader at using aluminum and getting excellent cost performance and tool life.
Okay, let's see. Is there any, Diane wants to know if there's any outgassing testing.
There's some, just like the best thing I can advise you is look at the base resin that you're dealing with. The outgassing is really going to be a function of the polymer, right? So if PCABS is going to outgas at a certain temperature and a certain amount, the PCABS based Premier materials are going to do the same. Same thing with the PEI, the Ultem based materials. You know, you want to kind of have your eye on what kind of outgassing. The fillers that we use generally don't contribute or reduce the amount of outgassing. It's all polymer based. So there's usually a pretty good amount of information on the internet that'll tell you what the outgassing of the specific polymer family is that you may be interested in. So that'll tell you if it's usable or not.
We have a lot of questions here from people regarding the different properties or cost and lead time. Just wanted to let you all know that all this information can be found on our website. So right there, parker.com/Chomerics. We have data sheets for all of our materials, as well as the ability to order some of our test kits, and they'll ship within 2 days. So just wanted to address some of those questions that we have coming in. We have a question from Alex. Pete, can this material be two-shot?
Yeah, and it can certainly be two-shot. I mean, and the secret to two-shot is making sure that the substrate and the overmold materials have a common polymer in general. So you could have like a PC substrate and a PCABS overmold. So as long as there's a common material, you're going to get good bonding. If there's not a common material, you're going to have some issues. Then you got to resort to mechanical methods. But you know, it's all about the polymer matching. If you can match the polymers, you're going to get excellent results for two-shot.
Okay, Yossi wants to know if these conductive plastics are available for 3D printing. No, they're not.
Oh, we wish they were.
We wish they were.
We're actually looking for people who can develop like the 3D fiber. I think in the future there's going to be, these materials are going to make the jump into 3D printing, but we're just not expert enough into the fiber development on this material yet. I know there's people that are doing like carbon fiber filled filaments now, and those are having good results. So I think it's coming, but we're not there yet.
All right, we've got a question from Larry regarding the processing of the Premier material. Does it require additional bolt-on hardware like heaters for the runner systems, or do we have processing parameters for injection molding?
Yeah, we have processing guidelines for all of our materials. We're pretty robust on that. We have processing guides for the PCABS family, for the Ultem, and for the PBTs, and they'll get you a good running start. And then you don't need any additional heaters. In general, if you can process that family of material in a standard injection mold for a product like what you're doing, you should be able to process our conductive materials without any issue. You might want to consider, if you're trying to achieve super cold, super fiber-rich surface, you might want to consider the usage of a chiller. You know, so that's going to like chill your mold temperature water, your water that's circulating through your mold, your temperature control. But that's pretty extreme. Most of the time, you can run what we call tower water, which is basically just going through a system where it's just radiating heat to atmosphere. And you know, most tower water and most injection molding facilities run somewhere around 80 to 90 degrees Fahrenheit. And we really haven't seen anybody have to go below that very often. Very rare.
All right, and thank you, Will, for letting us know that Prussia has 3D printing and fiber out of Europe. Let's see. Okay.
We might have
Slide
time for
20
one more question.
Slide 24, how tightly can an embedded fastener be reliably positioned? What about a tapped hole?
So that gets into tooling design. You know, if you have a very good tooling design, for instance, let's say you use a threaded insert. So the threaded inserts in general have like a plus or minus 5 thousandths ID tolerance. So most people use the ID to position the threaded insert in the XY axes. So that's going to be the limitations of your positioning tolerance for that. So whatever you have to design your core pin to the low limit of tolerance, and you have to allow for variation up to the high limit. And then in the Z direction, you can actually design it with a spring-loaded core. So you have a lot more flexibility. Say the length of your threaded insert is plus or minus 5 thousandths, for instance. That you can just use a spring-loaded core, and you should be able to accommodate any size that's within your standard tolerance.
Okay, if anyone didn't get their questions answered, feel free to reach out to us and we can definitely take it offline.
Exactly.
And if anybody has any ideas about how they want to use a material like this and they're not sure and they need some help on design and what's feasible and what isn't, I mean, that's what we're here for. Please reach out to us. We'll get with you and we'll take a look at your project.
All right. Well, thank you very much, Ben, Pete, and Sierra. We appreciate your time. Like we said earlier, all these questions, we can answer them and send them out to you folks. Within 24 hours, you will receive the recording of this presentation as well as the documentation that we discussed, data sheets, and link to our website where you can find more information about these materials. Anything else, Pete, Ben, Sierra? Think we're pretty good?
Have a great day, guys. Thank you for participating.
Yeah,
Yes.
Thanks everyone. Really good turnout.
Thank you all.
Thank you.